Let's take a look now at building solutions around singular points. In a previous section, we saw that for any second order linear homogeneous ODE, you can separate points into ordinary versus singular points. And we saw how to build series solutions around the ordinary points. Now let's go ahead and consider the singular points. Turns out that we can classify singular points further into subcategories. So here, let x equal x naught. Let's have that be a singular point of the ODE y double prime, still sticking in second order, plus pxy prime plus qx times y equals to 0. So second order, linear, and homogeneous. If x minus x naught times p of x and x minus x naught squared of q of x, if these are both analytic, at x equals x naught, then we say that x equals x naught is a regular singular point of the ODE. However, if multiplying that p of x by x minus x naught and multiplying that q of x by x minus x naught squared is still not sufficient to end up with those results being analytic, then we have what's called an irregular singular point. So otherwise, if this did not happen, otherwise x equals x naught is an irregular singular point. So for example, let's consider x squared minus 4 quantity squared y double prime plus 3x minus 2 y prime plus 5y equal to 0. And the question here is to classify the singular points. So first of all, we have to find what the singular points are, and then we're going to classify them into regular or irregular. Okay, so classify these singular points of this. Now remember, in order to classify ordinary versus singular points, we do need the equation to be in standard form. So here, this is non-standard. We're going to go and divide by this lead coefficient factor to give us y double prime plus 3 times x minus 2 over x squared minus 4 quantity squared y prime plus 5 over x squared minus 4 quantity squared times y equals to 0. All right, so here's our equation. Same thing as this, but now in standard form. And now remember, to classify the singular points, we need to find for what values p of x and q of x are not analytic. Okay, well, let's see, our numerator is polynomial, our denominator is polynomial. It's not multiplied out, but if it were multiplied out, it would be a polynomial. That constant is trivially a polynomial, and so is this denominator. So each component is itself a polynomial and therefore is trivially analytic. Every polynomial is its own power series. But we don't just have polynomials. We have the ratio of polynomials. We have a rational expression, which would not be analytic if it were discontinuous, and that is to say anywhere the denominator is 0. And so here, what we're really looking for is where x squared minus 4 quantity squared is equal to 0. Here you can take the square root of both sides to give you just x squared minus 4 equals 0. The square root of 0 still being 0. Here I could factor x plus 2, x minus 2. And so I get x equals negative 2 is one solution, and x equals positive 2 is the other. So this would give me the places where the denominator is 0, and therefore the expression is discontinuous by virtue of being undefined, and therefore not analytic. So these would be our singular points. But now the question remains, well, now that we have what our singular points are, what are they? Are they regular or are they irregular? Do we have one of each? So let's test them one at a time. Let's start with x equals to 2. All right. We know that we're going to have a singular point if we have either of these. Okay. The idea is going to be, well, how singular is it? That doesn't make any sense. Basically, how far away is it from being an ordinary point? Is it possible to just multiply by a single factor of what's wrong and correct that? Or is it such that I would actually need more than that to correct it? So here we would say, let's take our p of x, and we're going to multiply by x minus our singular point. Here our singular point is 2 that we're testing, so we'll say x minus 2. Okay, well, p of x is this function here. So that's going to give me x minus 2 times 3 times x minus 2 over x squared minus 4 quantity squared. Now, notice that this is factorable. In fact, we factored it before. The x squared minus 4 is, x squared minus 4 is going to be x plus 2 and x minus 2. But since this whole thing is squared, that means each of these would be squared. In our numerator, we have a 3 times an x minus 2 times another x minus 2, which we could write as x minus 2 squared. And notice that although x equaling to 2 was a singular point here because p of x was not analytic there, by multiplying that p of x by x minus 2, we have... well, we've essentially corrected the issue, because now what's left is a polynomial over a polynomial. Okay, cool. And it is still going to be discontinuous, but not at 2. I'm allowed to plug in 2 right here. 2 plus 2 is 4, which is not a problem. So by multiplying p of x by x minus 2, it went from, okay, the p of x by itself is not analytic at 2, but by multiplying by this simple expression, the result now is. Oh, but that may not be enough, because by definition, that has to happen not just to p of x, but also to q of x when you multiply by x minus x naught squared. So let's check that. Maybe that's not going to happen. So we'll take x minus 2 squared and multiply that by q of x, right there. That's going to give me x minus 2 squared times, well, I'm going to have my q, which is 5 over x squared minus 4 quantity squared, which, same as before, we can write that as 5 times x minus 2 squared over the x squared minus 4 factors as x plus 2 x minus 2. But then since that's squared, then each of those is squared. And just like before, hey, look, the problem just went away. This is still not analytic at a value, but that value is not 2. So by multiplying p of x by x minus 2, and by multiplying q of x by x minus 2 squared, we essentially got rid of the problem that was making this be a singular point. Okay, so you're saying it's not a singular point anymore? Well, no, it was a singular point because it originally was a singular point. But because it's a singular point that can be simplified to give us an expression where this product and this product and this product are analytic, then it's called a regular singular point. Right? So that's what we have here. This is a regular singular point. Basically, oh, yeah, it was singular, but not so much. Just a little bit of a tweak, and we were able to fix it so that it wasn't singular. That's called a regular singular point. What about the other one? Well, maybe the same or maybe different. Let's find out. We're going to take now x minus this number. Okay, x minus a minus, that's like saying x plus. So x plus 2 times p of x. Just like up here, just with a different number. All right, so that's going to be x plus 2 times, our p of x is, well, that's 3 times x minus 2 over x squared minus 4 squared. That numerator is 3 times x plus 2 times x minus 2. And that denominator is x plus 2, x minus 2, but each of these is going to be squared. And now you'll notice that although you do have some things that do divide away, it's not enough. Because what you're left with, after multiplying p of x by x plus 2, is still not analytic at negative 2, because it is discontinuous at negative 2. If I plug in negative 2 right here, I'm dividing by 0, and that's a discontinuity. In particular, it's an asymptote, but whatever. It's a discontinuity. And you cannot have an analytic function at its, a function is not analytic at its discontinuity. So here, even multiplying by, yes, it was regular just like this one was, but multiplying it by x minus 2, or in this case x plus 2, was still not sufficient to fix that. Oh, I don't even have to check the second one because it doesn't matter. If even one of these is not fixable, then that's what we mean by an irregular singular point. I won't even bother checking the other one because it won't matter. As long as this one is not analytic, that's sufficient to satisfy the condition of otherwise, right? Because up here, these have to be both analytic. We're going to consider now finding solutions around singular points. However, we're only going to consider solutions around a regular singular point. Solutions around an irregular singular point, we're not even going to consider anything like that. So we're just going to consider regular singular points. All right, so let's consider here an example of how to do that. Oh, I guess I should, before an example, we should state a theorem. And you know it's an important theorem when it carries a person's name. This is, at least to the best of my knowledge of the pronunciation, this is Frobenius' theorem, which gives us something similar to what we had previously about solutions around ordinary points. Unfortunately, singular points, even regular singular points, are slightly more complicated than ordinary points, as we'll see here. Or, well, rather, I should say they're potentially more complicated. In a nice case, they are every bit as simple, relatively speaking, as an ordinary case, as an ordinary point. However, with a singular point, it may be more complicated, as we'll see here. So let x equal x naught be a regular singular point. Again, we won't even consider irregular ones here. Be a regular singular point of y double prime plus pxy prime plus qxy equals 0. Then Frobenius' theorem states that there exists at least one solution. And this is where we will run into some problems. If you remember in a previous section, we talked about series solutions about an ordinary point. And there we had a theorem that said we're guaranteed to have two series solutions to a second order problem. Okay, that's nice. That's what we expect. Here, the best we can do is we can expect at least one. So maybe we'll have two, which is what we need to form a general solution, but maybe not. Maybe we'll only have one, in which case we'll have to work to find the other one in a way that's different from the building of a series solution that we've seen so far. We'll get to that later. So there exists at least one solution of the form. And although it is a series solution, there is one fairly major modification to it. And that is, okay, it's going to look just like what we're used to. It's going to be the sum as n goes from 0 to infinity of a power series C sub n x minus x naught to the power n, where again your x naught is just your center, whatever you're building your power series around. But although this would be the form of the solution around an ordinary point, around a singular point, you're going to have to multiply this by x minus x naught to some power. Reminiscent to the way that we fix, quote unquote, fix the lack of p of x and q of x being analytic. We multiply by x minus x naught to some power, first power, second power, or whatever. Here we do something similar. We're going to multiply by x minus that number to a power r. Here, although this is the way it's written in your textbook, many books also rewrite it this way, from 0 to infinity. Since these are the same base, you can just add their powers. So you can write this as Cn times x minus x naught to the power n plus r, where r is to be determined. Is to be determined. And where the series converges, for some interval r, or no, that's not the right grammar. It should be on some interval r. On some interval well, it wouldn't be r, it would be an interval between 0 and r. On some interval where x minus x naught is between 0 and r, for some positive r. In other words, you'll have a positive radius of convergence. Your textbook goes out of their way to write this in the form of an interval, but really all they mean is you have a positive interval of convergence. You're guaranteed you're going to converge around some point other than just your center. It'll converge for at least some small interval. Okay? A couple of notes need to be made on this here. Here, n is just the index, 0, 1, 2, 3, up to infinity. R is to be determined. To be determined by what? By the problem itself, or by the computation within the problems itself. That is to say, there is no r that's known ahead of time, and it's not related to the index. It's a number. R might be 7, and it won't change with the index. If it's 7, then it's going to stay 7 the whole time. Okay, so what? It's going to be just a random number? Well, it won't be random. It'll be dependent on the series itself. But what's more, and again, I'll write this as a note, r need not be like the index, where it has to be a positive number or an integer, 0, 1, 2, 3, 4. R can be any real number. It can be positive, negative, fraction, decimal. It doesn't matter. R can be any real number. So here, r need not be a whole number, the way you have for n. R is potentially any real number. Because R is potentially any real number, like consider the possibility, consider the different possibilities. If R is, let's say, 4, okay, well then this would be n plus 4 right here. Okay, well, instead of starting your polynomial at power 0, you would start at power 4. You cut off the first few terms. That's fine. But what if it's like 1/2? Well, n is always a whole number. Yeah. So if you add a half to any whole number, you won't get a whole number. You'll get a real number, right? You'll get a rational number. You'll get a fraction. Wait, but I thought power series always had to have these as, power 0, power 1, power 2. I thought power series had to have these as just integers. Yeah, that's right. So here, although we call the section power series solutions around the regular singular point, potentially, depending on what R is, our solution might actually not even classify as a power series, because by definition, power series should have integer powers. Also, you might end up with R being a negative number. So for example, -5. Well, then if n starts at 0, 0 minus 5 is -5. And then when n is 1, you'd have -4. And when n is 2, you'd have -3, and so forth. Wait, but again, I thought power series had to have positive powers. That's right. So in that case, that also would not technically classify as a power series. It would certainly be a series, and it would certainly have powers, but those powers might not be natural numbers or whole numbers from 0 to infinity. So although we're going to continue to use the phrase power series, here it is, you keep in mind that you will potentially get something that doesn't quite fit the definition of a power series. It will still be an infinite series, just not quite the ones we're used to. Then there's another note here which will make this part a little bit clearer. There exists at least one solution. Okay, but it's a second order problem. So I'm supposed to get two solutions and then take the linear combination, C1y1 plus C2y2. That's the solution that I expect for a second order problem. What happens if I have only one solution, though? Because my theorem promises at least one. If I have two, great, but what about just one? Well, since there exists, and here I'll underline this, at least one solution, you might not be able to find a fundamental solution set that has two elements, which is what you're supposed to have for a second order problem with two elements. Okay, so you only have one solution, so does that mean I just don't get a general solution? Well, no, because after all, we did see a way of, if you have one solution, you can create another one. Remember what that was called? That's called the reduction of order. In this case, take the one solution, right, the one solution you're guaranteed, and by reduction of order, the second solution is going to be y2 will equal to y1 times the integral of e to the minus integral px dx divided by y1 squared dx. That's how you would find the second solution in the case that you only got one. We're not going to do that. We're just not. We're not going to do that. Well, why not? Well, think about what that entails. Whether or not our solution ends up meeting the criteria of being a power series or not, it's still going to be an infinite series. Okay, sure. So look what that would mean. It would mean that our second solution would be, all right, you would take e to the negative integral of p. Okay, well, p is just a regular function. That's not really a big problem. Integrate that and then exponentiate. But then you'd be dividing by the square of a series, which means you'd actually have to manually go through and square out that series. Remember Cal 2? Remember how hard arithmetical series was? It was anything other than just addition and subtraction? Squaring or dividing by or multiplying by power series is just very tedious. Oh, actually, I guess you'd be doing both here, right? Because squaring and dividing. But then, once you finish doing that, you'd have to integrate that result and then multiply that result by that same series. That's exceedingly tedious, and it's just not something we're going to handle. So for the purposes of this section, although that is the way you would do it, we're not going to do that. We're going to pick problems here where we're going to get the two solutions that we need. If ever we did get one, this is the thing you should do, but we're not going to. All right? So let's take a look at an example. And this one, I went through a few different examples to find one that works nicely. That is to say, it gives you the two solutions the way you would want them to, and we don't have to go through any of this. So for example, let's go ahead and solve 2xy double prime plus the sum of 1 and x times y prime plus y equals to 0, with a series solution about the regular singular point 0. So here, this is one of the problems out of our textbook, and they're nice enough to tell you that it's a regular singular point. If not, you'd go through and check yourself, but they're nice enough to tell you. About the regular singular point, x equals 0. All right, so here we go. We're going to begin with the assumption that we have a series. Maybe a power series, maybe not, whatever. I'll avoid using the word power series since it might not apply. But even if it's not a power series by definition, it's still a series. So we're going to say y is equal to this series. N goes from 0 to infinity. C sub n, x minus x naught to the n plus r. And here we're going to need up to the second derivative, so we're going to take two derivatives. In this way, it looks very similar to, at least at the beginning, it looks very similar to solving around an ordinary point. All right, so let's see. We've got the derivative here would be the sum, y prime equals the sum of c sub n. I would take my n plus r and bring that down. So it's going to be n plus r. And then I'd have x. Oh, you know what? Since x is equal to 0, I don't even have to write x minus x naught. It's just x minus 0, which is just x. Not that that makes too much of a difference, but, well, it's a little less writing, and with what we're about to do, a little less writing is something that I would like to take advantage of. So here you would bring the n plus r down, and then subtract 1 from that. The same way you take any derivative of a monomial expression. And this is from 0 to infinity. Okay. And then we do it again. We take another derivative. Y double prime is equal to the sum, n goes from 0 to infinity, of c sub n times n plus r. And now we're going to bring down the n plus r minus 1. So n plus r minus 1 times x to the n plus r minus 2. So you already have a minus 1, but you're subtracting another one, so it'll be minus 2, x to the n plus r minus 2, and that would be our second derivative. And now we take those and plug them all into our problem. Okay, so let's see, well, that's going to give us 2x times the y double prime, sum from 0 to infinity, of c sub n times n plus r times n plus r minus 1, times x to the n plus r minus 2. Now, some of you might be wondering, when we looked at solutions around ordinary points, didn't these indices change? Like this one was 0 and this one was 1 or something like that? Yeah, I remember something about taking a derivative and then because you brought the number down, then plugging in 0 was going to make it 0. So we didn't use n equals 0 anymore. We used n equals 1 or n equals 2 or whatever was appropriate. Why aren't we doing that here? Well, check. If n is equal to 0, you get c sub 0 x to the r. Now, if you get n is equal to 0 here, you get c sub 0 times r x to the r minus 1. So this n being 0 doesn't make the whole thing 0. You're still left with an r. So even if you plug in 0 here, even though this part goes away, the entire expression is still not all 0. Same thing over here. If I plug in, if I didn't have the r there, plugging in 0 would make this 0. If I didn't have the r there, the n minus 1, plugging in 1 would make this part 0. Oh, but I do have the r. So even if I plug in 0 and make this go away, even if I plug in 1 and make this go away, I still have the r's left over. So since those are not 0, I don't need to get rid of those. So I've got 2x times my y double prime, plus I've got 1 plus x times my y prime, which is the sum from 0 to infinity, c sub n times n plus r times x to the n plus r minus 1, and then plus ry, which is the sum as n from 0 to infinity, of c sub n x to the n plus r, and all of that will equal to 0. All right, now, let's see. We're going to multiply. Same thing here. We'll multiply this into our sums. This factor here has a constant and a variable. So I'll separate those. When I multiply them in, constant with constants and variable with variables. So this will be the sum. N goes from 0 to infinity. The 2 multiplies all of these here. So I'll just put it right there. 2cn times n plus r minus 1. And then here, these variables will go together. X to the n plus r minus 2 times x to the 1. I'll add the powers, and that'll give me n plus r minus 2 plus 1 will just be minus 1. And now here, I actually have two things to distribute. I'm going to distribute the 1, and then separately I'll distribute the x. If I distribute the 1, nothing changes. I just write this again. Okay, so plus the sum from 0 to infinity, c sub n plus r, x to the n plus r minus 1. And then if I multiply by the x, well, the constants are still going to stay the same, but now my variable, I'm just going to add 1 to its power. That's x to the first, so I'll add 1 to its power. So that'll be plus the sum, as n goes from 0 to infinity, of c sub n times n plus r, x to the n plus r minus 1, but then I'm going to add 1, which will leave me just n plus r. Here, nothing actually multiplies times this one. I was just going to stay the way it is. It was just y, so I'll just bring that down. So that's going to give me plus the sum n from 0 to infinity of c sub n x to the n plus r, and all of that will equal to 0. So I've got this is one whole line, and this one just kind of wraps around like that. Okay, but well, I notice a couple of things here. These already combine. Notice these already have the same power, and they start at the same index, 0, right? N is equal to 0 to infinity, and these powers already match. Normally I have to work for that. Normally I have to go out of my way to make sure things match. Oh, well, they don't all match. Well, no, but these two do, so let me start with that. If I have something that's free, that's awesome. I want to do that. Same thing here. This is going to go from 0 to infinity for both, and both of these have a power x to the n plus r minus 1. You might look at that and say, oh, so is that what's going to happen when you're looking at solutions around regular points? No, that's just a nice coincidence. That could have happened around an ordinary point as well. Sometimes things just combine without you having to do anything to make that happen. When that happens, oh, let's just take advantage of that. So let's see. I can just combine those two here. So that's going to give me the sum, n from 0 to infinity, of, or let's see, I've got an x to the n plus r minus 1. That's a common factor here and here. So let me just combine the coefficients together. Let's see here. Oh, that's going to actually combine really nicely. Let me grab a different sheet of paper, and I'm going to do this to the side, because if I just say this aloud, it's going to be a little bit hard to follow, but it's not. It's a very basic arithmetic computation. It's just something that's hard to follow if we say it aloud. So let me go and do this off to the side here. So I'm combining just these two right now. Forget about the third and the fourth one. I have a sum as n goes from 0 to infinity. Now, notice my c sub n and my x to the n plus r minus 1. Those are the same thing. So those are common factors. So I'll worry about those later. Right? This and this are common factors. This and this are common factors between these two. So let me just worry about combining these things here. Okay. And again, this is very basic arithmetic, but if I say it aloud, it's going to be real hard to follow. So here, let's go ahead and do this. I'm going to multiply the 2 into one of these guys. And the one I'm going to choose is this one. You say, well, isn't that one smaller? Yes, but you'll notice that this one looks the same over here. So, so here's how I'm going to do it. I'm going to say 2 times n plus r minus 1. So that's 2n plus 2r minus 2. times n plus r. And then to that I'm going to add, so again, I'm not worried about the cn or the x to a power. Those I've just factored out for right now. I'm just looking at, okay, I've got this times this times this plus this. Okay, so when I multiply these three, I'm actually going to put these two together to give me 2n plus 2r minus 2. This one I just brought down, but I'm going to add an n plus r. Well, notice that that n plus r itself is a common factor, so I can factor it out. If I factor out an n plus r from those, I'm going to get just this stuff, and then if I factor out n plus r from this one, I'm going to get just plus 1. So here, those two numbers just combine, and so when I combine this one with this one, what I'm going to get is the sum, as n goes from 0 to infinity, of, when I combine, so the c sub n is a common factor. I'm just going to write it, c sub n. And then when I combine these three factors here, plus this factor here, what I'm going to end up with is n plus r times 2n plus 2r minus 2 plus 1 is just minus 1. And then this is a common factor as well, so I'll write that down. X to the n plus r minus 1. Notice that that's almost exactly the same as what this one was right here. All that really happened is I changed a single constant to merge these two together. And that's why I said this would have been hard for me to say it aloud in a way that was intelligible, but if I just write it, it's like, oh yeah, I'm just adding one. I'm just adding one more. For these two, it's a little bit more, a little bit simpler, because that's just going to be the sum as n goes from 0 to infinity. C sub n is a common factor, and all I'm doing is I'm taking n plus r and then plus one more. Right? I've got n plus r of these x's, and then just one more of these x's. Oh, then that'll be n plus r plus 1. X to the n plus r. So combining those two together, that's n plus r of this stuff, and then that's just one more, so plus 1. All right, so I've gone from 4 series down to 2 series, which is a nice, condensation of our problem here, and it didn't take any actual changing. It just took a little bit of arithmetic on our part here. Okay, but unfortunately, the free combinations are over. So now we actually have to work to combine these two. They do start at the same index from 0 to infinity, but these powers are different. Oh, but we know how to fix that. We can go ahead and fix this. What power does this start at? Oh, well, let's see. If I plug in 0, this one starts at power r minus 1. Here, if I plug in n is equal to 0, I start at power r. Okay, so then this one actually starts at 1 more than this one does. This one starts at r. This one starts at r minus 1. Okay, so then there's this extra term that this one has that this one doesn't. Right? Because like if r is 10, here I start counting at 9, here I start counting at 10. Now, whatever r is, I'm counting, this is 1 less. Okay, so then this is one extra term that this one doesn't. Oh, but we know what to do in that case. We just strip that one off. So what we're going to do now is we're going to just say, okay, well, let's add, ooh, what happened to my camera there? Everything went really bright. Okay, there we go. That seems to be, I think my autofocus just freaked out there for a second. Okay, where were we? Oh, yes. So I'm going to plug in n is equal to 0. Okay, well, let's see. That'll give me C0. And then 0 plus r, well, that's just r. And then 0 plus 2r minus 1. Okay, well, that's 2r minus 1. And then if I plug in n is equal to 0, I get x to the r minus 1. Okay. Oh, but now I've gone ahead and plugged in n is equal to 0, which means I can take that one off of my sum, and now I can call this the sum as n goes from 1 to infinity of all the same stuff. The rules don't change, just where I start counting does. I already used n is equal to 0, so now I would start at n equals 1. So n goes from 1 to infinity, c sub n times n plus r times 2n plus 2r minus 1 x to the n plus r minus 1 plus the sum n from 0 to infinity c sub n times n plus r plus 1 x to the n plus r all equals to 0. Okay, now notice, where does this one start counting? Well, let's see, that 1 and the minus 1 cancel, so this starts counting at r. Power r is the first power. Here, this one starts counting at, n goes away. Oh, this one also starts counting at power r. Okay, so by taking out that one term here, now this one starts at r, and this one starts at power r. Okay, cool, so now they match. Oh, but they match in where they start counting, but they don't match in their index. Right? This is going from 0 to infinity. This is 1 to infinity. One other thing to notice here. Okay, if n is equal to 1, I've got an x to the power r. Okay, sure. Here I've got an x to the power r. Okay. But even if n is something else, if n is 4, if n is 10, whatever, pick your favorite number, you're still going to have x to the some number plus r. Here, you're going to have x to the some number plus r. And here, you have x to the r minus 1. Okay, so x to the r is a common factor. We can pull that out. So here, let's write this as, I'll just write the x to the r on the front. And this will give me C0 times r times 2r minus 1, x to the minus 1. Notice if I take out x to the r, that just gives me x to the minus 1. Multiply these two together, the powers add, you get r minus 1. Plus the sum from 1 to infinity of c sub n n plus r times 2n plus 2r minus 1, x to the, and again I'm factoring out the x to the r, so now I just have x to the n minus 1. And then here, sum as n goes from 0 to infinity, c sub n, n plus r plus 1. And again, I'm factoring out x to the r, so I'm just left with the x to the n. Okay. So once again, now let's check to see where I'm starting from. I factored out the x to the r. So now, when n is equal to 1, I just started x to the 0. And here I started x to the 0. Okay, so now this looks a lot more like what we had with ordinary points. So now, let's go ahead and combine these by rewriting the indices. Remember, to rewrite the index, you want to set k equal to whatever your power on your x is. And with the x to the r gone, that's now a lot more familiar looking. Here, if k is equal to n minus 1, then that means n is equal to k plus 1. Over here, the k will equal to whatever the power is, which is just n. Okay, so there, I'm not even doing any computation. Just replace all your n's with k's. Okay, so that's going to give me x to the power r times c sub 0 times r times 2r minus 1 x to the minus first plus the sum as k goes from 0 to infinity, because if n is equal to 1, 1 minus 1 would be k is equal to 0. Okay, k from 0 to infinity, c sub, well, my n is being replaced with a k plus 1. So c sub k plus 1 times k plus 1 plus r, k plus 1 plus r, times, let's see, that's going to be 2k plus 2, but then minus 1. So that's just 2k plus 1. Plus our 2r. I'll say that one more time. Here, n is k plus 1. So when you plug that in, you get 2k plus 2, 2k plus 2. Oh, wait, no, but it's not plus 2 because I'm subtracting 1. Oh, so it's not plus 2, it's just plus 1. So 2k plus 1. The 2r, I just brought that down. X to the, and now our power is just k. Plus, and then over here, you don't really need to think about it. Just replace all the n's with k's. There's no arithmetic or even thought involved. It's just a straight up substitution. But now, hey, look, everything starts at power 0. I forgot my x to the k, didn't I? There we go. So now everything starts at power 0, and the indices go from k equals 0 to infinity for both. So now, finally, I can merge these together. So this will give me x to the power r times c0 r times 2r minus 1 x to the minus 1 plus a single series, k goes from 0 to infinity, of the x to the k is a common factor, so we can go ahead and factor that out, leaving us just the coefficient, which will be ck plus 1 times k plus 1 plus r times 2k plus 2r plus 1. I'm going to factor this one out, so I'll write it at the end. So now I just got to add this part, plus ck times k plus r plus 1. Okay, so I've added this coefficient plus this coefficient plus this one. And then the x to the k is the common factor, is equal to 0. Just like that. Okay, so once we're here, we can now use this for two different things. One, obviously, we can use this as a recursion. Okay. Obviously? Well, yeah, because that's exactly what we do with an ordinary point, right? So with an ordinary point, the whole purpose of condensing everything down was to use the coefficient to create a recursive algorithm to find your coefficients. And here it seems to be doing the same thing, because look, this is k equals, when k equals 0, I have x to the 0, and then x to the 1, x to the 2, x to the 3, x to the 4. You only ever have one coefficient paired with one power of x, which means that I don't have anything I can combine with. There's only one time when x to the 0 shows up, and that's it. You'll never see that again. So if that's going to end up being 0, it's because its coefficient was 0. And same thing for x to the first, x to the second, x to the third. Any power of x will only show up once. And so if I'm adding together different powers of x, and they're all adding up to 0, well, there were no like terms to combine, which means they were 0 to begin with. Okay, so I can use this for my recursion. But also, and maybe even more importantly, here's an equation that I can use to solve for r. Because after all, these are x to a power starting from 0. This is x to the minus first power. That's not like any of these. These start from 0. This is minus 1. Oh, but it's also being added to all of this, and you're also getting 0, which means this must also equal to 0. So this, right here, gives me that, well, let's see, C0 is an arbitrary constant. It can be literally any number, so obviously that's not what's making things 0. And x is a variable. It can be any number, so it's not what's making things 0. It's got to be these factors that are making things 0. So from here, I get that r might equal to 0, or maybe it's that r is equal to 1/2, because 2 times a half is 1, minus 1 is 0. The two solutions to this equals to 0. Oh, but those were the r that I needed to find according to Frobenius' theorem. Frobenius' theorem says that this value r is not known. It's determined by the series itself. Oh, here it is. We just found it. These things right here, there's a few notes to be made on these. First of all, a little vocabulary. These are called the indicinal roots. The roots of the index, I guess, right? The roots that tell you what index you're using, what r you're using to modify your index, right? To modify your power. So these are called the indicinal roots. And however many of these you have will be how many solutions you get. The number of these will tell how many series solutions we will get. Because remember, Frobenius' theorem guarantees us at least one solution. So maybe we'll get one, or maybe we'll get the two that we need. Oh, if we only get one r, then we'll only get one solution. But if we get two r's, then we'll get the two that we need. All right. So now we know what our values of R are going to be. Okay, that's nice, but now what? What are we going to do with those? Well, we know what R is. Plug it in. We now know what R is for these different values. Now, what you could do is you could plug it in right now and then try to separate it out and get your recursion. Or you can just get your recursion and then plug it in at the end. I tend to prefer the second one because once you have the recursion, plugging in a single number one time will get you what happens here, and plugging in that other number a single time will get you what happens for this case, rather than to have to plug it in all of these separate times. But again, it's a matter of choice. You can either plug it in now and then simplify your recursion, or you can simplify first and then plug in. I tend to prefer simplifying first. So let's go ahead and get our recursion, a recursive algorithm for our coefficients. Here we're going to take this coefficient will equal to 0. Okay, so that's going to be c sub k plus 1 times k plus r plus 1. I'll reorder this to put the 1 at the end, times 2k plus 2r plus 1 plus c sub k times k plus r plus 1. And that coefficient must equal to 0 because we know that's not the thing that's equal to 0. So it's got to be these. Okay, well, with a recursion, it's best to take whichever instance of your coefficient has the greatest index, in this case ck plus 1. That's a bigger index than c sub k, k versus k plus 1. So we're going to solve for c sub k plus 1. So let's subtract that over. So I get c sub k plus 1 equals, I'm going to subtract that over to give me minus ck times k plus r plus 1. And then since I subtracted this over, now to get this by itself, I'll divide these two away. So I'll divide by k plus r plus 1 times 2k plus 2r plus 1. And hey, cancel, cancel. So we get that our recursion, c sub k plus 1, will be the opposite of c sub k over 2k plus 2r plus 1. Oh, but if we have two different values of r, I actually get two different recursions. So now, plug in your different r's, your different r values, to get different recursions. All right, well, I have two r values, so I'll get two different recursions. Here, if r is equal to 0, that's the one possible r, then I get that my recursion is c sub k plus 1 is equal to negative c sub k over, well, this part just disappears since r is equal to 0, and I just get 2k plus 1. On the other hand, if r equals to the other possibility, which is a half, then we get that c sub k plus 1 will equal to negative c sub k over, you plug in r as a half, so 2 times a half is 1, plus 1 is 2. So 2k plus 2. Kind of anticlimactic, right? They're almost exactly the same, just off by a constant. But that difference is enough to give you two distinct series solutions. So now, here we go. We can take C1, right? And that's when k is equal to 0 to get C1. Okay, well then that's going to be negative c sub 0 over 2 times 0 is 0 plus 1 is 1. If I find C2, well, that's going to be the opposite of the one right before it, the opposite of C1 over 1 times 2 is 2 plus 1 more is 3. Oh, but C1 itself was this stuff. So it's going to be the negative of this stuff, which is just going to be positive C0 over 3. If I find C3, well, that's because k was 2. Right? When k is 2, I get C3. So that's going to be negative C2 over, what did I say? K was equal to 2, so that'd be 2 times 2 is 4 plus 1 is 5. Oh, but C2 itself was C0 over 3. So I'm going to want the negative of that. Oh, but then I'm dividing by another 5. So that'll be 3 times 5. And let's do one more. If I do C4, well, that's because my K was 3. So that'll be the negative of C3 over 3 times 2 is 6 plus 1 more is 7. Oh, but C3 itself was this. So it'll be the negative of this. The negative of a negative is a positive. And then I'll be dividing by an extra 7. So now instead of 3 and 5, I have 3, 5, and 7. Yeah, it's alternating, right? If C0 is positive, C1 will be negative, then positive, then negative, then positive. And the denominator seems to just be kind of like a factorial, but using only odd numbers. Isn't that a weird looking pattern? It's a factorial, but with only odd values. Okay, what about this one? Well, pretty much the same thing. My C1 here is going to be C0 over, let's see, whatever the K is here, double it plus 2, that'll give me 2. So I get negative C0 over 2. Now C2, okay, well that means K is equal to 1 if I'm finding C2. That's going to be negative C1 over 2 times 1 is 2 plus 2 is 4. Oh, but that C1 itself is the negative of C0 over 2. So I want the negative of that negative, which is a positive C0 over 2. And now that's being divided by another 4. If I find C3, that's because my K was equal to 2. So it's going to be negative C2 over 2 times 2 is 4 plus 2 more is 6. But now this C2 itself is this stuff, right? C2 equals this. So I want the negative of this. And then I'm dividing by an extra 6. If I take C4, that's going to be, C4 is because K was equal to 3. So I get negative C3 over 3 times 2 is 6 plus 2 more is 8. Oh, but then that's going to be the negative of C3, which is just this stuff. C3 equals this stuff. And if I want the negative of this stuff, that just makes it a positive. C0 over 2 times 4 times 6. And then I need to divide that result by 8. Okay, so there'll be an extra 8 on the bottom. Oh, so this is like the other half of the factorial, right? This is all the odd numbers multiplied. This is all the even numbers multiplied. In general, right here, and I don't need you to find the general rule for this. As long as you have the coefficients, that's fine. But here, this one actually is relatively easy to spot. Here, notice that whatever your index is here, your C1, if you do negative 1 to the n, that'll give you the correct sign. Because negative 1 to the first power, that's a negative. Negative 1 to the second power, that's a positive. Negative 1 to the third power, that's a negative. Fourth power is a positive. Oh yeah, so that does give me the right plus minus plus minus. I guess I should say power k, right? And then my numerators all have C0s in them. And then my denominators are all just odd numbers multiplied together. Notice that where I stop is you take your index, multiply by 2, and then minus 1. All right, double 1 is 2, but then minus 1 is 1. Double 2 is 4, minus 1 is 3. Double 3 is 6, minus 1 is 5. Double 4 is 8, minus 1 is 7. So it is going to be 1 times 3 times 5 times ... And where you end is whatever index you have, whatever your k is, you want to multiply by 2, but then subtract 1. And that's going to be the last number. So this right here is the rule for any arbitrary c sub k. So instead of doing it with a recursion, now I actually have an explicit formula for those c sub k's. For these, I have a very similar looking one. It's also alternating, right? The C0 is positive, C1 is negative, positive, negative, positive. So these c sub k's are also going to alternate using the form negative 1 to the power k. But now, well, let's see, I guess I do have a C0 here, don't I? So C0 over, and now I'm multiplying the even numbers. So 2 times 4 times 6 times ... And I end at whatever the index is times 2. Here, when I had C4, I ended at 8. C3 ended at 6. C2 ended at 4. It's whatever the index is doubled. So although you don't need to find the general form of this, it's enough if you actually just get these coefficients manually like this. But this one seemed clear enough to me that I was willing to take an extra 2 minutes to explain what those are going to look like. So in the end, we have our coefficients for 2 different series, and so we are done. We can now write out our answer. Thus, our solution is going to be y equals C1 yeah, that's fine. C1 times, and you can do this one of 2 ways. You can actually write out the coefficients themselves, and you can say that's, I guess I have a C0, don't I? So C0, that's the common coefficient there. So it's going to be C0, and then 1 minus 1x, I guess I can just write minus x, minus x, and then plus 1/3 x squared, and then minus 1 over 15x to the third, and then plus 1 over 15 times 7, that's 105 x to the fourth, plus dot dot dot, plus, and although here we have the same C0, we're using C0 for everything, we can't rely on those being the same. So here C0 is an artifact of the fact that we handled this as if it were a completely separate series, but it actually is part of a bigger solution. So don't use C0 again, because just like we've seen since chapter 2, these are arbitrary coefficients. They don't have to be the same. So here I'll say C1, even though it's C0, but that's just because we treated this as if it were a totally separate series rather than the complement to this one. So here I'll say, instead of C0, I'll say C1. Or, maybe I can use K0. I can use a different symbol. Just make sure these aren't the same symbol. Times, and then let's see, we've got, what have we got? We've got, we've got 1 for the first one, but then we've got negative 1/2. Right, negative, we've taken out the constant, so it's just going to be negative 1 over 2. Oh wait, that's not 1, is it? Because remember, in this case, our r is 1/2. So over here, where our r was equal to 0, we went ahead and said, oh, well, since r is equal to 0, our powers are just n, meaning 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But when r is equal to 1/2, our powers are not going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're going to be 0 plus 1/2, 1 plus 1/2, 2 plus 1/2, 3 plus 1/2. So this very first one isn't 1x to the 0, it's 1x to the half. So this is going to be 1x to the half plus, let's see, where did my numbers go? Right there, it's going to be 1x to the half. And then minus half x to the, minus is the next one. So minus 1/2 x to the 3/2, and then plus 1 over 2 times 4 is 8, x to the 5/2. Notice that's just 0, 1, and 2, but I'm adding half to each one. And then minus 8 times 6, that's 48. So 1 over 48 x to the 7/2. And then plus, what do I have here? 48 times 8. That's 384. So 1 over 384 x to the 9/2. Dot, dot, dot. On and on and on. And if you leave it like this is a perfectly acceptable answer because that is the series. But since I actually happen to have the rule for any term, you can actually even write this in a more convenient series form. That is in a sigma form. That is to say, I can write this as C1 times the sum as n goes from 0 to infinity of, well, I have my rule right here. So it's going to be negative 1 to the power n Here I wrote it as k, but my final series I tend to write as n because that's the way series are usually written. But you can keep k if you prefer. This would be c1, negative 1 to the power over 1 times 3 times 5 times, c0, times dot, 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 all the way until you get to the 2n minus 1 right here in your denominator, times x to the power n, plus, and then again, these are also all c0s, but it's supposed to be a different coefficient, so we'll call it just something else. We'll call it c1, times the sum as n goes from 0 to infinity of minus 1 to the, well, we've already taken out our constant, so it's minus 1 to the n over, and then it's going to be 2, 4, 6, 2 times 4 times 6 times dot, 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 all the way till you get to your 2n, and that's going to be x to the n plus 1/2. If you want to write n plus 0 here, that's fine, because that is the r value that you got, but n plus 0 is just n, so you just leave it that way. But this one, n plus r, would be n plus 1/2, so that one you actually have to do right. You do have to write that way. And so here we get a series solution with two series, one of which actually is a power series, since it uses only whole numbers from 0 to infinity. And this one, although it is a series, it's not technically classified as a power series. But whatever, that's a technicality of vocabulary. We still have a series solution to our original Cauchy-Euler equation. This Cauchy-Euler equation has that as its series solution. Finally, for this topic, I want to expand a little bit more on this note that I gave earlier on. I mentioned that because there exists, since there exists at least one solution, you won't always get a case that works out nicely where, oh, I have my two solutions and that's it, I'm done. I mentioned that it is much more tedious and it's prohibitive to do it manually, by hand. There is software, there are computer-aided techniques to help you find these solutions, but that's not part of this course. We're not a course in computer science or computation, so computer-aided methods are just not part of what we do. So because of that, anything besides this kind of result is just not something we can realistically hope to find in a reasonable amount of time. That being said, that doesn't mean you shouldn't know what the solutions would look like if we were to take the time to find them. So right here, you'll note that we have two solutions that form a fundamental solution set, and therefore we can form a general solution this way. However, that need not necessarily be the case. So there are three cases possible for series solutions about a regular singular point. The first case is the one we just did. So case number one, if the additional roots R1 and R2 are not equal to each other, if they are distinct, they're different numbers like we had here, 0 and 1/2, distinct. Oh, one of these days I'm going to have to learn how to spell. Distinct, and R1 minus R2 is not a positive integer. Then you get two linearly independent solutions then you get two linearly independent solutions to form a general solution. And this is just like the example we just did. There's one thing here you might note. X1 minus x2 is not a positive integer. What do you mean by that? If they are positive integers, look what happens. If the difference is a positive integer, basically what you would be saying is, okay, this would be x to the n minus a half, and this would be x to the n minus 3 halves, or something like that, where the difference between 1 half and 3 halves would be a positive integer, 1, 2, 3, 4, 5. Okay, well, what's wrong with that? Well, if you had n plus a half and n plus 3 halves, that's the same as saying n plus a half and n plus a half plus 1. Okay, so if all you're doing is adding 1, then you're just offsetting your series by a single step, by a single count. In other words, these would be exactly the same, except one would start at 0 and one would start at 1. Okay, so they wouldn't be linearly independent. They would have all terms being equal to each other except 1. And having a single term be different does not make your expression be linearly independent, because literally everything else, all other infinite number of terms, would be exactly the same. So in that case, you would not have linearly independent sets, which means you do not have a general solution made up of those two linearly independent sets. So in the example that we just saw here, our results were distinct, and when you subtracted them, 0 minus a half or a half minus 0, whichever way you wanted to go, you did not get an integer. Okay, so that was case number 1. What about case number 2? Well, case number 2 and case number 3 are going to be the ones that we're not going to go through, but again, it doesn't mean you shouldn't know what they would look like. So if R1 is not equal to R2, the two indecisive roots are not equal, but you do get a positive integer, so R1 minus R2 is a positive integer. Then we get a series solution. Then we get, I guess I should be a little more, a series solution is correct, but let me be a little more emphatic about it. We get one series solution, and there exists a second solution. And this is probably the most vague statement I'll make this entire course. There exists a second solution which may contain a logarithmic term. Which may contain a logarithmic term? What do you mean may? Does it or does it not? And what do you mean a logarithmic term? Like the log of something, or like the square of a log of something? The log of x, the log of r? What do you mean? Well, that's about as detailed as we get. It may contain something that has a logarithm. Which is another reason we don't go too far into this, because this one actually is a pretty vague result. A logarithmic term. That is to say, y1 equals to sum, as n goes from 0 to infinity, of c sub n x to the n plus r, where, again, that's the kind of solution we got in our first example. But then our second solution would look like, might look like some constant times your first solution times your y1, times the natural log of x plus the sum, as n goes from 0 to infinity, of b sub n x to the n plus r2, where r2 would be the second series, the second indecimal root that you found here, where your b sub 0 should be non-zero. Here, to make things even worse, this c might be 0. In other words, this logarithmic term might be there, it might not. It might be a different multiple of a logarithm. And because of the way logarithms handle constant multiples, it might actually be the log of a power of something instead. So that's why I said it's kind of a vague statement. And here c might be 0. Which again, those mights are what cause the uncertainties here. But if there is a solution, it probably looks like a series solution plus the original series solution times a logarithm. Probably, maybe. And then finally, case number 3, and that's if both of your roots are the same, or in other words, if you only have one root, then there do exist two linearly independent solutions. The linearly independent solutions where your first one is just like what we got in our example. It's going to be some sum as n goes from 0 to infinity of a coefficient x to the n plus r, where that r is going to be the r that you found. There's only one that was found. And your y2 is going to be y1 of x times the natural log of x plus a sum as n goes from 1 to infinity of b sub n x to the n plus r1 or r2 or whatever. They're the same. So this one is a lot less vague. It tells you you'll definitely have a logarithmic term. Here, it might be a logarithmic term, and maybe it has a coefficient, or maybe not, or maybe it's not even there. Who knows? This third one's a lot more direct. Yes, that's exactly what it's going to look like. However, finding those results, again, as I mentioned earlier, would require reduction of order, since cases 2 and 3 require reduction of order. It is not realistic to do an example or to have it be on an exam or an assignment. We wouldn't have you do these by hand. To do a problem that falls in either case by hand. So rest assured, they don't show up on the homeworks, they don't show up on the exams or anything like that, but this is for your own edification, so for you to see, oh, here is what this would look like should we take the time to actually go through all that. But that's it for this topic, and that's it for this section. Should anybody have any questions or comments, please feel free to reach out, and I hope everyone has a nice day.